Hello everyone and welcome back for a new Databricks video. In this demo we are going to take a look at Mosaic AI Vector Search, how we can use this in a practical example, and we are also introducing Reranker. Reranker in Vector Search will help us improve the agent quality by ensuring that the agent gets the most relevant data to perform its tasks. So let's jump in. Before we get started, let's check a little bit what vector indexing is, just a small introduction to it. So it's basically a key component of a vector database that helps to significantly increase the speed and the search of processing similarity search. In simple words, if you think about a supermarket, you basically know where the fruits are. They have their own department there, their own section, and you pretty know that apples are going to be found near bananas, for example. On the same time, if you are checking for magazines or for newspaper, you have to check other section of the supermarket because they are all clustered around the same meaning. The same happens also in a vector store database, where these similarity search are found and calculated. So this is why we need a Databricks vector store, so that in our PDF, for example, PDF information in our context, we can find similar information fast and retrieve that information with higher precision. Now let's jump into the demo. I'm going to switch to my Databricks account where I already have a cluster online here, which contains the machine learning runtime. And let me walk you through what we are going to demonstrate here. So basically we'll have a delta table which contains already the data chunked, and also the embeddings. So the embeddings in this case not fully managed, but is self managed embeddings. We have done the embeddings before. We are going to create an index, a vector store index. We are going to have vector store compute there. I'm going to show you how to do that. Creating an endpoint there. And on the right side, we have the user who's basically querying the data. And we're going to use the same embedding generation that we have done it before, so that we compare in the end apple with apple. So let's start with the first step, create a self-managed vector search index. For that, we have to go to catalog and select our table. So our table is in Gen AI catalog, schema, archive schema, and the table it's called PDF text embedding. Actually, let me show you the sample of the data, so that you have an idea what we are talking about. All right, so data is looking like this. So I have in my volume here all the PDFs required. These are the PDF names, and every PDF is then split it into chunks. Then for every chunk we have the content, and we have the embeddings on the right side column. Great, what we have to do now, we have to go here to create and check vector search index. This is how you create the index. In order the index to work, then you need first to go and create compute vector search. So let's do that. Compute vector search and click create endpoint. Let's give it a name here. ArchiveX vector store. I'm going with the standard and click confirm. Now it's created successfully, but it's still in status provisioning. Let's wait until this vector search endpoint reach online state. Until then, I'm going to show you a little bit here in the catalog. So we have the Gen AI catalog and the schema. What is interesting is that all of these things that we are creating, like index, vector store index, These are treated like normal assets in Databricks. So this means that it complies with the overall governance that we have it in Unity Catalog. The same permissions applies as for volumes as for tables. So once the vector store index is created, you can just go and create permissions, create policies, and work with a normal asset in Databricks. Second very important thing is that those assets are on top of your lakehouse, which is very beneficial because the context is already there. You don't need to glue any other tool to reach that information, that corporate data that you might have it in your lakehouse. So now let's check the compute power again. Vector search still in status provisioning. So our compute is now started. The general purpose cluster is also online, so we can dive into the code. Before that, I'm going to show you how this looks like. So the vector search, this is how the UI looks like, and it says here that we don't have any indexes until now. This is the next step. We are going to create that. For that, we go to catalog, Gen AI, I have schema, and select the table again. And on the right side, we go create and click vector search index. We give it a name, PDF IX from index. We have to select a primary key. Columns to sync, I will synchronize the PDF name, content, and embedding. And in the next step, I have to choose between compute embeddings and using existing embedding column. Now, because we already calculated and generated the embeddings before, we are going to select use existing embedding column, which is column name embedding. Here we need to enter the dimensions of the pre-compute embeddings, which is, in my case, this number here. Then we have to select the compute. This is exactly the compute power that we have created before, the vector search. And we have two types of synchronization, triggered and continuous. Now, with triggered, this means that if our embeddings are changing, our delta table, this will not be automatically synchronized with our indexer. Now, the alternative is to choose continuous. And when you choose continuous, this will be automatically synchronized with your vector search database. For this demo, I'm going to choose triggered and click create. Great, so now our index is in status provisioning. As you can see here, you'll find the index as table here under your schema, which is great because you can, as I said, you can use the same permission and the same governance that applies to tables. You can go here to permissions and grant users permission to refresh and to select this kind of object. You can distinguish that because it says here, having here another symbol, and there are also specific information that are only related to the index, which is the index type, delta synchronization, source table, and the service endpoint. Great, now we have the index. Let's go to our code. So in the notebook, I already have my cluster attached. First, we are going to install some libraries. And in the meantime, if we check the architecture picture, so basically we have our delta table, we now have the indexer, we have the vector search database, and we can go and use those assets to create our use case. Okay, so now I have the libraries installed. These are some errors that are not related to our use case about length chain. So let's continue with our endpoint. First, I'm going to define my endpoint name, which is exactly the one created before. And the next is a function that is checking that the endpoint is ready. In the next cell, we are going to verify that function, and it says that the endpoint is available and is ready, which is exactly what we have here. This is basically how you retrieve the status of it. And the next part, we are going to connect the delta table with the vector search endpoint. Our catalog is called GenAI, schema is this one, and this is the table name. We can also give here a full name for the index. Remember that we already have an index created, which is this one here. But if you want to create one index programmatically, this is how you can do it. You can define, also we are defining here another name. It has to be a different one. We are defining a function which is checking that the index is ready. And the next function is checking if the index exists. And because we defined here and give it another name that doesn't exist yet, if we are going to check if and trigger our function, it will say, of course, false, because that index that we defined here doesn't exist. If I change it back to PDF X, and run the function again, then it will say true. Let's try to create another index, this time programmatically. So this will be our index 2, which doesn't exist yet. And in the next step, if doesn't exist, then we are going to create it programmatically. And this is where you are going to leverage this create delta sync index, which is part of the client that we have defined here before, vector search client. So we are going to leverage this function here, create delta sync index, to create another one. The same information we can pass here. We have the triggered, we have the primary key, which is the column called ID, and embedding vector column, which is embedding. And if we run, this query should create a new vector index. So it's creating the index on the same endpoint. And after it's creating it, then I should be able also to see it here in the UI. It's already there. If we go inside, then it will do the initial synchronization between our table and the index. Okay, now it's online. We have it here. Everything is synchronized. And next we are going to do a similarity search on the content. Let me show you first what we are going to search for. So one of the files that we have it there as a source is this one here, GPTs are GPTs. It's saying here some abstract. We investigate the potential implications of language models on the US labor market, right? And then some introduction and some other information. So it's pretty complex. It has also pictures inside, paragraphs, annotation. And what we are going to search. So this is one of the files. If we go to the volumes here, these are all the files that we have. One of those files is the one that I showed you. And what we are going to search is, for example, what is the implication of large language models on the US labor market. For that, we are going to use MLflow deployments, and we are going to store the response in this variable, and then do the embeddings for this query. Remember, we have to use the same endpoint for the embeddings, the same endpoint that we use for embedding our source data. Next, we are going to get 5 documents that are similar. So 5 chunks or documents that are similar. For that, we are going to use this similarity search function. And we are going to print the result. All right, so now it found here the file, which is exactly the file name here. And if we scroll down, the next chunk is this one, to get a sense of how quickly. So it's the same file, but another chunk. The same file again, but yeah, another chunk. So this is a lot of context about this topic. Now, we don't know exactly which one is more closer to what we are looking for, to our content, right? We mentioned here what is the implication of large language models on the US labor market. And for that, we might want to have a re-ranking in our search result. Re-ranking in this case means that whatever you found here in these results, do a re-ranking based on the content associated with the request. So basically, it's going to give me a probability of 60%, of 70%, that this content here is exactly the content that I requested. So for this re-ranking, we are going to use a very light library. It's called FlashRank. It's an open source re-ranking library. First, I'm going to extract my path, my local path. I'm going to import the ranker and re-ranking request, and then print the result. As you can see here, I'm passing as parameter here the question and those passages that he found it earlier with the similarity search. So the similarity search is the token-driven, the embeddings-driven search, and this one is re-ranking based on the context. Now you can see here the result. So it's the same file, of course. To get a sense of how quickly this is ranked as the first one, it has like 60% accuracy. So he ranked as 60%. I believe this was the first one in our initial list. No, it was the second one, this one. It was this chunk, this text. So the second chunk here was ranked as 60%. And if we scroll down, we'll find the next one here. It's only 51%. And so on. So in this case, it means that we are closer to our context and to our expectation if we are going to retrieve this chunk here. Because this is exactly the question here. In the initial phase of similarity search, all of the paragraph here, the 5 that we restricted here, the 5 retrieved, they are about this topic, but which one of them came closer or is getting closer to our expectations? And according to the model, this one here, it has a higher probability that is closer to what we expect. And this is how you can use a vector search index on Databricks. This is how you can use rerank. There are also other libraries that you might to check it. FlashRank is the open source one that we are using in this demo. Again, we demonstrate here how to create a vector search. And if you go inside, you will find the 2 indexes. Interesting here is that you will also find the metrics for that index. You'll see here a spike in requests per second. This is where the synchronization was made between our index and the delta table. I hope you enjoyed this lesson. Looking forward to seeing the next section. Until then, enjoy Databricks.